Hello, my name is Juan Pedro Carbonell Rivera. I am a PhD student of the Polytechnic University of Valencia in Spain. In this presentation entitled Drone Mapping, Photogrammetry based on unmanned aerial vehicles, we will introduce the use of drones to obtain geospatial data. In this video, we will provide a brief introduction to the photogrammetry theory that enables drone mapping, highlighting the most important concepts for the correct implementation of photogrammetric acquisition using drones. Throughout this presentation, I will give some flight planning tips and address several questions, including what is photogrammetry, how does drone mapping work, how do UAV photogrammetry software function, and finally we will conclude knowing some UAV terms. The collection and processing of drone mapping is divided into 5 steps: study of the work area, flight planning, flight execution, obtaining of point clouds, orthophotos, and elaboration of maps, and map interpretation. In this presentation, we will focus on the first 3 steps, while in 2 other videos we will focus on the last 2 steps. Before the realization of our photogrammetric flight, there are some aspects that are necessary to take into account. For example, understand and comply with regulations, clearly define objectives and flight plan, choose the right flight location, assess risk and prioritize safety, develop an optimal flight plan, check weather conditions, and perform a pre-flight checklist. To perform a photogrammetric survey with a UAV, first, control points are positioned on the ground over the study area, and their centers are measured with GPS. Next, a flight is conducted in which there is at least a 70% overlap between the photogrammetric shots, both frontal and transversal, whereas in complex environments higher overlap is required. There are a wide variety of planning software available on the market that can be used depending on the brand and model of drone that you have. For example, DJI Pilot, Pix4D Capture, or UGCS. In this sense, a great variety of different types of flight can be performed depending on your needs: corridor, grid, spiral around an object, etc. Afterwards, the dataset undergoes processing in photogrammetric software such as Pix4D, Agisoft Metasafe, Photomodeler, Reality Capture, or OpenDroneMap. These software solutions allow users to generate different products such as orthomosaics, point clouds, or 3D models. Some projects may involve a post-processing phase, where it is possible to refine these products into more advanced outputs like works, thin surfaces, and more. But why are ground control points taken? Why it is necessary for there to be overlap between images? To address these questions, let's delve into photogrammetric theory. Following Wolf, DeWitt, and McClone, photogrammetry is defined as the art, science, and technology of obtaining reliable information about physical objects and the environment through processes of recording, measuring, and interpreting photogrammetric images and patterns of record radiant electromagnetic energy and other phenomena. In the next slides, we will explore how the application of photogrammetry to UAV flights allow us to obtain point clouds, 3-dimensional models, and orthophotos. First of all, let's define some terms commonly used in the field of drones. The first of these terms is ground control points, which are defined as points on the Earth's surface with a known location used to georeference UAV data. Secondly, image overlap is defined as the coverage overlap between consecutive images captured during a flight plan. It is important to differentiate between frontal overlap and side overlap. Finally, the ground sample distance represents the physical size of one pixel on the ground, and it is calculated by multiplying the flight altitude by the pixel size of the sensor, and then dividing the result by its focal length. This slide explains the process of creating a georeference dense point cloud from sets of images. Photogrammetry software employs multiple images with sufficient overlap to determine the spatial location of a point. The process initiates with feature detection using algorithms like SIFT. These features, also known as key points, are then matched across different images, linking the same point in various frames. Hence, it is essential for the images to have both frontal and transversal overlap. Following this, the structure from motion algorithm is applied, succeeded by scaling and regioreferencing to obtain a three-dimensional cloud of points. The video in this slide serves as an example of these key points. During this step, the coordinates of the ground control points taken before the flight are added, establishing a relationship between the control point and the T-points generated in the point cloud. Multi-view stereo is subsequently applied to densify the point cloud, which can be further refined through image clustering, resulting in the georeferenced dense point cloud as the final product. Once the point cloud is obtained, 3D models can be derived from the triangulation of the cloud, and orthophotos can be generated from these models. From a practical point of view, the software available in the market automates these tasks, sometimes leaving the user with only the option to select the level of detail for the resulting product. And with this, we end this video. If you have any questions, you can contact me by email. Thanks for your attention.